Hello, and welcome to today's webinar on the Industrial Internet of Things, Fundamentals for Open and Secure Design and Deployment, brought to you by Control and Bedrock Automation. I'm Paul Studebaker, Editor-in-Chief of Control Magazine and ControlGlobal.com. Before we begin our presentation, there are a few housekeeping issues that I'd like to review. On your screen, you should see several primary sections. The upper left or audio control section allows you to adjust the volume of this presentation. Just hover over the audio volume control and adjust the volume to your preference. To the right in the largest section is where today's presentation slides will be displayed. Under the slide window, you'll see a chat section where you can chat live with fellow audience members. At the left of the slide window is the questions and answers box, where you can type a question for the presenter at any time during today's webinar. We'll get to as many of these questions as we can during the Q&A session following the presentation. If we're not able to get to your question today, or if you have a question after the webinar has concluded, we'll respond later by email. The handout button at the bottom of the presentation slide contains links to several resources, including the full set of speaker slides, a white paper describing best practices for securing an industrial control system, and an evaluation of Bedrock Automation's open, secure approach by ARC Advisory Group. At the bottom of your screen, you should see additional icons. For other features, by hovering over each icon, information about the icon will be displayed. If you are having technical problems, you can type in your question or concern in the questions and answers box, and one of our technical engineers will assist you. If you need a better view, you can enlarge a section by clicking on the box in the top right corner of the section next to the X. If you accidentally close out a section, you can get it back by clicking the Restore button at the bottom of the screen to the left of the icons. This webinar will be archived, and we encourage you to direct coworkers to the recorded presentation. At the end of the presentation, we'll ask you to complete a very brief survey to give us the feedback we need to improve our webinars. Our speaker today is Albert Rooyakkers, founder and CEO of Bedrock Automation. Albert has 130 patents in system and semiconductor design, 20 years of automation experience, 13 years of semiconductor experience, and has been founder and CEO of Bedrock for 5 years now. I will turn the controls over to Albert.
Thank you, Paul. And thank you for all the people that are joining us today. I really appreciate your time and will do my best to impart in some information and some of our ideas and knowledge in this very important subject matter. The premise, as was the paragraph that drew you to this day today, it's the IIoT is a convergence of sensing, actuation, network, and computation technologies that are converging at the edge of process automation. It's really quite a disruption that's being compounded by the cloud computing technologies that are making great strides in automation applications. The result of all of this is a flat architecture that's full of risk and reward, and I'd like to cover some of those risks and rewards through the rest of this presentation today. So fundamentally, what is it that's enabling this value and the availability to the automation users is the fact that big and small companies are really converging and innovating and delivering the tools and the technologies that's making this real. No longer just a probability. This is very much the direction that automation is heading today. So this is who I am, as Paul said. Don't need to say it again, but what's important is, why did we start Bedrock? Why did I decide I want to do this? And one was, first and foremost, the industry is due for a refresh, and it has been a very, very long time since someone was able to take a blank sheet of paper approach to this and solve some intractable problems, and in particular, it's cybersecurity. and have some real fun doing it and create an open secure automation platform that would be available to everybody in the market. So while that's a picture of me a few years ago, this is a selfie I took just yesterday, and this is what happens when you decide to try to disrupt such an incumbent industry. It really is hard work, and that's kind of what I look like, but that's not really how I feel. But it is a lot of work, and it's been a lot of fun. So let me just share some of that energy with you. I'd like to start also with a preamble, an outline of some definitions and why does it matter, what's making this happen, what is this going to look like, what does it look like now, what are the barriers to entry for the OEMs and the users, and summarize it in the end. Not necessarily in exactly this order, but you'll get it when we'll understand when we get into the meat of it. These two charts represent the data summary from a comprehensive Morgan Stanley survey and report on the industrial Internet of Things from just a couple of years ago. And even then, 70% of the respondents said that the Internet of Things strategy is important to their company, but there's a whole lot of contingencies to the adoption. And you can see that cybersecurity, standardization, their installed base and legacy technologies, investments, skilled workers, and so on. These are all the issues that are of great concern. So we're going to touch on a few of them. And if you look at some of the most important top issues, you can sort of infer that some of the other issues will start to look after themselves, and this becomes a real probability, a real possibility for users. So let's look at calibrate ourselves on some of the terms. So what is the Internet? Well, everyone knows what it is, but maybe not. The fundamental property of the Internet is that it's a set of standardized protocols that allows everything to communicate to everything. It's really that's the fundamental basis of it. And it's generally assumed that you are on the Internet using either public or private networks, almost entirely public networks now. So that's the first stake in the ground. What is a thing, the industrial thing? Well, the things in the industrial thing is the sensors, actuators, and controllers, fundamentally, that measure, compute, and regulate a physical process, whether it's a factory automation or a process automation. What is the edge? And we've heard that term a lot. It's not really a place. The edge is the earliest place. It's not a fixed place, but it's a place where data and computing power and communications all converge in the most meaningful way. And that means that the edge kind of floats up and down vertically, up and down in architecture, depending on the installed base, depending on the age and the architecture that exists in place. So presumptions are that the industrial Internet of Things is really a synonym or another way of saying digital transformation, and we'll explain that, and that should make more sense. The cool thing, I think, is that it really is becoming a force function for this IT-OT convergence. There's been a lot of press and a lot of discussion, and there's a lot of consternation or strain in organizations to figure this out, and it's going to figure itself out because it sort of happens naturally. And there's a general presumption and real truth factor to that cloud computing is becoming and will be an integral part of Internet of Things, and the Internet of Things exploit this broad global cloud architecture that allows access from anywhere to virtually anything. So these are the broad stroke building blocks that make this all real. So what is the cloud? Well, the cloud is not only is it on everyone's PowerPoint and it's on every piece of marketing information you see, but it's not a place. It's an idea, and it's a suite of computing technologies that scale vertically, horizontally, and literally infinitely. It's an elastic computing resource that allows on-demand computation, which is computation and data storage, at the lowest possible cost. The costs are falling through the floor, and it's almost mind-boggling. The tools are things like clusters, virtualization, containers, orchestration. These are the tool set, and go to the web services companies, AWS, Google, Amazon, others, Microsoft. You will see a growing suite of tools that exist as part of the cloud. It is an ability to allow access in combination with the internet to allow everything and anything to be available always. If you don't believe that's true, you know it's true as soon as your mobile phone is connected. It is almost certainly on the cloud, and you can get anything, anywhere. Now, the use of cloud technology in industrial applications is really dependent and defined by bandwidth, latency, and security. These are the three factors that will determine to what degree and where does the cloud most effectively work. It supports open SCADA anywhere as a thin client on any piece of glass. It's bring your own device, BYOD. That's fundamentally where it is and where it will definitely go in the future. So anyone that's been granted access to information will be able to get it on any piece of glass anywhere in the world. What is the fog? It's not just the smoke outside in the cloudy days. It's not. It's again an abstraction of the computing between the edge where that may exist and the cloud, which could exist someplace else. So it's just, again, it's not a place, it's an idea. So you have the internet, the cloud, the fog, the edge, and the thing. And so you put all those together and you can start, building, putting building blocks. So at any rate, let's see now. Did I forget anything? No. I would say one point is on the cloud as far as scalability. This is an important point in embedded space. Cloud scales down, and it is scaling down rapidly to the point where a cloud, the fundamentals of a cloud, which are computing and storage and computation and embedded applications, they are and will continue to be on a single chip, and that means that they can be anywhere. So let's go to the next slide. What's making it happen is obvious simplification and consolidation. These two graphics are from ExxonMobil. Their open process automation efforts to bring simplification to automation. And modern technologies around hardware, software, network computing, these enable dramatic simplification of a traditional Purdue model that you see on the left, or the ISA 95 model. This is 20 years old, and it was built for proper network and data segmentation with the best of technologies 20 years ago. Well, that doesn't necessarily make any more sense. And you can greatly simplify the network by combining these classic layers. So simplification denotes obviously reduced cost and complexity because you just have less stuff lying around. You get increased reliability because there's fewer things to break. You get decreased latency and increased performance. And you have an increased homogeneity of the software, the tools in the networks, engineering tools, software tools. So all those things, big check boxes, immediately has an impact to the user on cost, on capital cost and lifecycle cost. So what does it look like in a more detailed fashion? Again, this is from the OPA group, the user group. This is some of their earlier architecture drawings. And the OPA group is represented by some of the largest users of automation in the world. So if you take a closer look at it, you can see from their vision from just a few years ago, it really could have been called the industrial internet of things for petrochemical, with an early call out to the cloud, because you see a very flat real-time bus. You see the combination through gateways and connectivity of legacy and modern technologies. All of it's based on at the network layer on Ethernet. You see one layer above it, business and operations coexisting in some form of a data center. So it's got all the terms and all the architecture around the industrial internet of things, and an early call out to cloud. Now, I would say that even in the few years since this has become public, or since they've made their vision clear, you can see that the technology is scaling and converging such that you can have on-premise, private, and/or public clouds, and you can have even embedded device-level clouds where these technologies move down. And so you have the thing, you have the connectivity, you have the cloud, you have the applications. This really is, a version of a unified digital edge and various forms of cloud, and put it together, and you have the industrial Internet of Things for petrochemical. So it's really one and the same. Now let's just take a look at it in another way, and start looking at it in a building block. Now there's no dynamics to the side, so just bear with me. So at the bottom of the slide is a process. You're making cheese, you're making cars, you're making petrochemicals. It doesn't matter, because connected to the process is what I would call the digital edge. And what's important is the digital edge is already saturated with beautiful devices, sensors, analyzers, actuators that have been digital, that have microcontrollers and microprocessors, have twisted pair and digital communications for 20 years now. The industrial market has been way ahead on this. And so these things exist. Now, new sets of capabilities, whether it's in power or in control, all of these devices are part of the edge that require the fundamental building blocks, and we're going to go into that in a minute. That's the digital edge that's connected to your process. And you can see that the mediums can be, here on the left, you see a new smart digital power supply. You see some form of a transmitter, a sensor. You see a valve and an actuator, and some kind of gateway, PLC, local control technology. So these connect in virtually any kind of physical medium. It can be wireless, it would be secure, it can be twisted pair, it can be copper, it can be fiber, it can be Ethernet, it can be HART, it can be Profinet, DeviceNet. It doesn't really matter, because all of the connectivity needs to be able to mix and match, and it does. We've been doing this for decades. We know how to do that. And where there's non-Ethernet like twisted pair, well, these twisted pair, obviously they connect through the local gateway device, and immediately you get to Ethernet. So at that point, depending on the architecture of the user, you are now engaging in a public/private network. If you have the Internet of Things, you can deploy a public network if you address the issues of security and standardization and communication. And as I've said up to now, you can and do have cloud-like aspects. You have computation, communication, data storage, and tools that allow these functions to exist right at the edge. Or it can be one level up in the user's onboard data center. But across any one of these tiers, which is only for the user a two-tier architecture, sort of a level 1, level 2, everything else disappears. And then you have a public cloud where big data analytics exist. But an operator on any kind of a generic piece of glass, that operator can be an operations person, an engineering maintenance person, and that person can be anywhere. You can be standing right in front of the equipment. You can be in your control room, in your truck, in your corporate offices. You're going to see the same data on the same glass. This is what it looks like deployed. And so you can imagine that security becomes quite a big issue. So let's take a look at some of this here. At the digital edge, you're going to do sensing, control, and actuation. You're going to have open, secure connectivity in real time, ultra low latency, and intrinsic security. What would you do with it? You would run a local historian or logging functions or sequence of events, machine-based analytics, and others to be determined. The layer above it, you could call it the fog, but or you could call it a private cloud. This is most likely on-premise, and you have a combination of private and public networks. You have defined role-based access, constrained resources because it's on-premise, You don't have as elastic a resource as you would in public cloud. What would you use it for? You would use it for plant-based historians, plant-based analytics, advanced process control, and secure SCADA. This is how it comes together at that level. In the public cloud, you would have on-demand, fully elastic resources with universal access anywhere geographically. And here's where, again, secure SCADA, the same human interface, the same operator tools, but you would have truly physical remote operations, data warehousing, global data analytics, global machine learning, AI, other applications that would be more relevant there. So that's what it looks like in the deployment. And is it possible? How do you get there from here? Because this seems kind of cool, and you could do some cool things with it. So let's take a look at the apps. What is the killer app? There's plenty of them. I'm going to touch on them. One is all data, everywhere and anywhere. That gives you fully remote operations for maintenance and engineering and operations and management. Most certainly, you would have to solve both the security problem across the board, across the networks, and you'd have to have a clear definition around role-based access and role-based access control. Those tools exist, that technology exists. When it's done, it works beautifully. Predictive maintenance and remote diagnostics. This is not something new, but definitely this is where the money is. And it's dependent, the degree to which you can get remote diagnostics will depend on how much horsepower, how much digital, how much modernity do you have in your sensors and actuators. But even in legacy infrastructure, there's a lot to be taken from the good old-fashioned instruments with a little bit of digital horsepower and a heart signal. You want to get that securely to the internet, to the public networks, and to the cloud, and you can start to do a lot of cool things with it, understanding what's going on far away and being able to know what to do when you get there. And the amount of time and money you save in truck rolls and human resources, it can be staggering. So analytics, data analytics are well defined as well. People have not, this is not something that's new to people in process automation. We've been learning how to make these exothermic and explosive processes and machines that are invaluable and dangerous. We know how to make these things work safely, and we know how to extract every last dollar out of a distillation column or out of a furnace. We know how to do these things. But running analytics that are easier to get to, that can run anywhere, and that can start to push the envelope on what's possible, then these are the applications that the Internet of Things can do. And then dashboards. It's the whole ease of use process. We're very familiar now with the home buttons on our mobile devices. You don't go to school to learn your mobile device. It's intuitive. And security, analytics, machine learning, AI, these applications will become more and more intuitive, more and more like a dashboard. And this is how you're going to distill the information in the most optimal way. So let's take a look at these barriers. Let's get to some of the prime technologies. One is standards. Well, one of the most important things is software, and what's really cool about the industrial instrumentation and automation field is that the 61131 standard has been 20 years in the making, and it has become a de facto standard. Whether it's OPA or the major users in the European market and Asian market, 61131 has really become the de facto standard. So finally, we have a tool set that took decades to define, has a wonderful library of tools, and you can do anything with it. You really can. And it's done. So that train has left the station, that cake has been baked, and you can start to build from it. So what do you have to do now? You have to solve the security problem to ensure that an open engineering tool set can be cryptographically authenticated to a user, to a workstation, to a controller, to a site, etc. And to the thing in the end. You want one tool, and that tool is programming, configuring the digital valve, the digital power supply, the digital controller, the digital gateway. It's one environment, and that is true. It's working, and it works. There's technologies, we've proven it, and you can make it incredibly and intrinsically secure. The other important thing is that it should be free. The software engineering tools need to be free. They are free. We're making them free. Others will, and that's a major, major difference. So you're free to develop, free to innovate, free to test with simulation and other things built in. This is how you are going to unleash innovation. Now, anyone with a good idea that's got the right experience and background can sit down with a standardized set of tools and make that tool work, and they don't have to invest money in order a king's ransom in order to get what they want to make it work. So that piece of it is fundamentally done. Now the other piece is standards, open standards on protocols and connectivity. This is a very important piece of it. Again, to revisit, look at a Rosemount transmitter, a Fisher valve, and anything actuator. These things have been digital with smarts and communications for decades. So it's important that we find a way to protect and enhance those technologies. I don't believe in this rip and replace. I don't think anyone should be sold down the river that, oh, I'll never get to the Internet of Things unless I spend a king's ransom and a bazillion dollars and rip everything out. That's not true. It's just not true. There's too many smart ways to get these protocols and these devices into a gateway, into a client, into a device, a PLC that can immediately take that legacy protocol and convert it to a secure standard Ethernet. It exists, and these devices at the edge have to support any number of these protocols. It has to be there, so you don't have to try to buy one device versus the other. Good digital technology, good design will ensure that an appliance, a device, a PLC, some modern device can interconnect and bring these legacy buses to a modern bus architecture that can be accessible to the Internet. It can be done. The second, if you look at, say, that device in the middle, this is once again an example of a modern edge device. Well, these edge devices, they behave in a very traditional way. It's a power supply or a UPS or something of that sort. It does what it's supposed to do. However, it has direct and secure Ethernet connectivity, which gives it Internet connectivity. It has advanced sensing and diagnostics. It has secure downloads and secure boot. It is built the way a modern device should be built. So now you can, in brownfield and greenfield projects where you have consumables like a UPS, the batteries go dead. Do you want to buy a standard UPS like you did before, or you buy one that's digital and secure? You make it do what it used to do, but now you can plug it into the Internet and you can start building a hybridized configuration. So you're putting small, low-cost appliances that connect to modern and legacy technologies, and all of these things start to bring you to the Internet. There's low-hanging fruit everywhere, and this connectivity story is here. These are well-proven technologies, so you can find them now. This is becoming commercially available. Now, these devices also need to support protocols that are typical of connectivity on these private and public networks. They have to connect through Ethernet and support OPC UA, MQTT, and DDS as a minimum. So you have these three things, you really are well on your way. And most importantly, these network protocols need to support security, TLS, PKI, and authentication and encryption. Again, it is now commercially available. All right, so let's talk about security. It must be built in. Going forward, you must pressure the users out there, the vendors out there. You must pressure your R&D. You must pressure your OEM. You can build it. You can build it secure. Let me just jump forward here a slide. We'll go back to that other slide. We've written a lot about this and published this. I don't want to belabor this point. We've been here before. You can download our white papers, and we talk extensively about it. But at its core, it is it starts at the microcontroller. It starts at the computational engines that are in these embedded devices. And these technologies were hardly available 5 years ago, but now it's commercially available, and this is not extremely expensive digital components. We've designed them and built them ourselves. So the closer you get to the core, the closer you get to that engine, it's more complicated and expensive to engineer these basic security. You see these 6 or 7 line items there. These are the building blocks of making secure computation. But once you do that, you're closer to zero marginal cost to deliver and execute on this technology. So when you start at the smallest building block and start building out, you can make this stuff intrinsic, and you can do it very, very cost effective. It's quite expensive and complicated to engineer, but it's the lowest possible cost to deliver these capabilities to the user. So there you have it. You start with the building blocks that are now there. Now you add to that, you see here a whole series of different technologies that are built into a device. And it doesn't matter what that device is. It's a thing, it's on the process. It has to have anti-tamper, a secure RTOS, secure communications, and the list goes on and on. This is all stuff that can be done. And when you build it, you can object it, you can modularize it, and it becomes more and more efficient to use a combination of these technologies when you're building anything that's going to be at the edge and as an industrial product. So the second major building block is metal. Now, to be secure, everything that's industrial and electronic, everything has to be metal, and it has to be sealed for anti-tamper. That's a fundamental. Now, the tooling and design, making a product, is a little more expensive when you're building it out of metal versus plastic, but in volume production, it's fundamentally a wash. We waste more aluminum in the U.S. than you can rebuild our air fleet every week or something. It's cheap. Aluminum is throwaway. So once you invest in the technology to design it out of aluminum, it's the same cost as plastic. So transmitters and end devices have been dealing in metal for years because that's closest to the process. It has to be, handle explosion proof and non-incentive areas. So you just have to push it up a notch and make sure that these devices are made out of solid metal. If you don't, you cannot deal with the tamper detection and tamper prevention that's required. The third piece of the puzzle, at the edge, is probably the most difficult nut to crack for vendors, which is building a secure supply chain. And for most people, it means you have to rebuild it. And rebuilding a supply chain means from a component and from a code traceability, and shielding this code and these building blocks from a massive attack surface and attack vectors. Otherwise, you really can't put a system together that's secure. Now, in addition to that, security at the edge with these devices is about keys. And unlike you and I, where we have a dozen keys in our ring for our home and our car, if you're going to have hundreds, thousands, tens of thousands of devices, you're going to have tens of thousands of keys and certificates and users and others. You have to have a key management system that will allow a seamless and easy to use application invisible to the user. Now let's be clear that this technology has been well proven in aerospace and military and in e-commerce. So this is not something that we have to wait for something to be invented. The e-commerce fundamentals of security are being used 1 billion times a day in transactions online. The military and aerospace industries have been doing this for decades. So it's just taking the best and brightest of technologies and reapplying it in the most appropriate way. So what is the net result? With these fundamentals, you unleash the kraken of security, and you vaccinate your system, your edge, just like you vaccinate yourself biologically. When you defend from a biological virus by vaccinating that every cell in your body, and you can intrinsically defend yourself against the biological virus, you do the same thing with the digital world. You vaccinate it at the transistor level with the technologies we've touched on today, and you will become intrinsically secure. So when industrial things are built with these standards and technologies, the cloud and the edge will marry virtually transparently, because you're using the same crypto, the same authentication and certification, the same public key infrastructure, the same TLS tunneling. It's e-commerce security down at the embedded space. So when you build from the bottom up and the cloud from the top down starts to come in the middle, the interconnectivity and the security becomes seamless, and it happens by default. So what does it matter? Why? What's the whole point of all this? Well, you got to follow the money. And you got to know that if you want to know what the technology that's going to win, will it save the user money? And most certainly it will. It's an absolute given, and it's being proven by the early adopters today. Why? Because you see the classic 1, 2, 3, 4, 5, 6 life cycle cost parameters. The white papers have been written around this for decades. The cyber defense is one of the newer cyber. The cost of cyber is now embedded in most companies as part of their overall life cycle operational cost. So with the Internet of Things devices, the architecture, the fundamentals we're talking about today, you get a smart, flat architecture that's based on standards across the board. Lots of hardware goes away, and redundancy, when it's designed right, becomes affordable. Most people put redundancy in DCS applications, but not in PLC applications. Well, the quote-unquote PLC or the gateway or whatever that appliance is, if it's designed right, you can make it redundant for maximum availability. You can afford to make that investment from a user and from an OEM. And that maximizes the availability further, because so much of the rest of the infrastructure is gone. So you get the best possible availability and open standards. Intrinsic security and access, intrinsic secure access anywhere. So any operator based on role-based access defined, you can coexist, or you can exist on zero trust public networks, and you will certainly optimize your labor cost. If a particular engineer that knows a particular amount of intrinsic knowledge on a piece of machinery, that person can be notified and instantly gain the access that he needs to say, he or she needs to say, this is what I think the problem is, get this person or do that or that, and you can contain the damage, you can minimize downtime, you can minimize risk, maximize safety. That's how it works, and this isn't just bibble babble. This is how it's working. This is the real world. This is why it'll work for you. Remote diagnostics and predictive maintenance, again, labor efficiencies, maximum return on invested capital, faster speed of response. You want to use this technology in a pragmatic way so that you can protect your current investment with smart, small improvements. You can bring legacy technologies that are digital into a secure Ethernet environment and get it to the internet. There's many smart, cool things to do, to do here, where with moving into this direction, you unleash a bottleneck of data that's sitting out there on the edge. In many cases, is with a 20-year-old heart, DP cell from Rosemount that's just loaded with diagnostics and secondary measurements, or a smart motor control on Profinet that's just begging to be called to the internet in a secure way so you can understand what's going on with that motor. So it works. The cloud will work seamlessly in this environment, and with monsters like Microsoft, Google, Amazon, IBM, and the list goes on and on. These are the e-commerce, cloud providers that are pushing into the space, and you have the OEMs, Honeywell and others, who are creating their own private clouds to extend those services. It's all good news. This is all good. It's driving costs down, driving capabilities up, and it will bring the OT and IT convergence together, because it's not as complicated when it all comes together. It's an elegant, intuitive interface from the human factor, and much of the technology disappears. You're not managing the usual chaos of switches and routers and firewalls and defining parameters of what is IT and what is OT. It doesn't really matter. It's all the same thing. So in summary, we can look at these, what we think the value proposition is. I don't want to read them out. You can read this and download these slides. What I want to say is that this is not future speak. This is not something that might happen. This is something that is happening. There are ways to leverage your installed capital. Greenfield and brownfield projects can be rethought with really cool technology that allows you to get yourself to the tall poles. Hardware costs should and will be lower. Software tools should be free. They are free and they should be. These are what you should be demanding of your suppliers. The cloud is here. Resistance is futile. The power of it and the capabilities of it are very relevant to the automation world. So go at this thoughtfully and carefully. Look for that low-hanging fruit, the 80-20 rule. You don't have to rip and tear everything apart. You can go at it smartly and build your future on it. So when I say the future is now, use it or lose it, I'm not saying this in kind of a smart aleck way. I mean it in that you be smart and be brave, and don't imagine that these tectonic shifts don't need to happen or won't happen to you, because they are happening, and the early adopters will have a significant financial and technical advantage. The tech of IIoT and cloud is all caught. It's all off the shelf, commercially available. Most of the most of the catch-up, not ketchup on your French fry, is catch-up. The catch-up is the vendors that are building the technologies at the edge. You need to pressure the suppliers to think different and do a better job. And I would say fundamentally three things. Hardware should be infinitely more capable at a same or lower cost than today. Software tools should be free, and security should be intrinsic. So it can happen, it will happen, and thank you for your time.
Well, thank you, Albert. Great presentation. We have several very interesting questions, and while we start answering them, the audience should please feel free to continue to send us more. Our first question, Albert, is how far away are we from the edge computing model that you propose?
How far away from it? I would say that we're here now, and we've been here for a while. I think there's a lot more horsepower and capabilities. The computation and the functionality that exists at the sensors and actuators have been doing a good job for decades. The difference is, how do you most effectively get these legacy technologies connected on a public network in a secure and open manner? That's the task. And any new or greenfield or brownfield project, there's plenty more choice now to buy a traditional motor control, a traditional power supply, a traditional instrument, or buy one that's more properly enabled with security and Ethernet connectivity. Those choices can be made today.
Okay. We have a question about, with IIoT, what is the future of the AMS vendors?
What's an AMS vendor? Sorry, acronyms.
That would be asset management system.
Oh, okay. What's the future of asset management? Ooh, boy, that's a good question. I'm not an asset manager supplier, so if I answer this question, I'd probably fake it and I'd do a bad job. So let me think about that, and I'll get back to that person in writing.
Okay. You had one slide relevant to this. Is the Purdue model history? Is it no longer relevant?
Is the Purdue model no longer relevant? Well, I would say that the Purdue model is relevant to the billions and billions of dollars of infrastructure that's out there that's interconnected and working in a model similar to the Purdue model. So it is relevant and will be for decades. It's not as relevant when you're system architecting today, because you don't need all these networks and all these boxes. You just don't need it anymore. So I don't really think about it in that perspective, and don't think much about it. We just think about what we've built, and you just don't need to consider it as much anymore. You still have good design for network segmentation and for area segmentation. There's the usual good practices, but a lot of that pig iron, those networks and those interfaces and switches and routers and so on, they've just converged and consolidated into one box, and so the horsepower and the networks are different. So to the user, to people that are using it, obviously you're going to maintain your systems and your technology as long as possible. But for new designs, it's not really relevant, no.
Okay. I'll add a comment that I think the ISA is working on a new version because of IIoT. But we have another question. Yeah. Where does OPC UA fit in the future of secure automation?
Well, OPC UA really is a foundational piece of it. It is basically the leader today. OPC UA is converging with the capabilities of, say, DDS or PubSub. You're going to see that. Then you get the best of both worlds. It is the future. We use it extensively. They've done a decent job of their security, and that's all working. So, yeah, it is the future.
Okay. Here's another question. How is embedded cybersecurity different from what other control vendors are doing?
Well, if you have not built a product that has all of these secret sauce, you can't make the product do one simple thing, which is secure boot. So if it's built intrinsically secure, every time an infinite number of startups and shutdowns in any orderly or disorderly way, you will not corrupt the ability of that device to boot in a secure mode. So the firmware and the boot code are contained within a device that is physically and digitally anti-tamper. And so that's the difference. If you haven't built it that way because you didn't have the tools or the technology when it was designed, then you have to mask it. So you're going to put, procedures and technologies, gateways, data diodes, and other things to try to protect it. And it's the best you can do, and I'm not saying you shouldn't. And a lot of times, by just doing some very fundamental things, you're going to improve your security. There's lots of simple best practices. We wrote another white paper on that too, for recommended best practices for any legacy installation. So if you have not built it in a modern way and it doesn't boot securely and it isn't anti-tamper, you have to do other things to try to protect it to the best of your ability. And there's lots of good ideas and lots of things you can do, simple things to, catch the tall poles. So that's the difference.
Okay. We have another question. What is necessary to maintain the security of the Bedrock systems? Are there ongoing services offered by Bedrock?
No, because you don't have to do anything. We now don't charge for for software. For software tools, we don't charge for software maintenance. Software is built into the cost of the hardware, and security is software once the hardware is built. So there's nothing you need to do. You start it up and you interface it. All the cool things that go on in order to create secure boot is transparent to the user. The user turns it on and the light goes from red to green or blue or whatever the status is. It's transparent to the user. It all happens intrinsic to the technology.
Wow. Pardon me. We have another question.
I wrote that down. Wow. Paul, I wrote that down. It said, wow, WW. I like that.
I apologize.
No, that's good.
Will closed-loop control ever migrate fully to the cloud?
Oh, man, that is a really good question. That's a very, very, very important question. In some cases, it already has. And, again, it's a function of the architecture for a cloud. First of all, where is the cloud? Is it a private cloud, a public cloud? Is that embedded right in the machine? And it doesn't really matter. The machine that is conducting the closed loop control already has, all these capabilities. Let's just keep in mind that today a decent, device in the field has multi-core 32-bit computation architecture that exceeds a state-of-the-art DCS or PLC controller, and that's in a handheld device. That in the next couple of years will migrate to quad-core 64-bit server class capabilities in just the next couple of years. So there's almost nothing you can't do. You have more horsepower than you had in an entire refining control system sitting in the palm of your hand in a motor control or a smart valve. That's going to happen. So where will the cloud be? It'll be wherever it needs to be. So if that cloud, if that data storage or that AI application where you have some serious big data analytics, well, how big does the data need to be? If you're doing machine analytics, you care about the analytics of that machine. You want real-time data every thousands of times a second. So it already is happening. So probably the question is, what about a cloud application? What about, you're running your control off-premise on a public network on AWS or something? Will that happen? Well, I think some people are already doing it. It's going to be a function of whether or not that public network has the latency, the security, and the uptime that's required as if it was a network right on your control system. So it's happening already. It doesn't fundamentally matter if that cloud is somewhere on-premise or on-device, and it will be a function on a user-by-user basis on whether or not the network, the public or private network, meets the latency and performance and security that's required of a network. And then in that case, that's up to the user to decide, and people have already made that decision.
All right. We have a question. Are there sensors and actuators on the market today with the ability to work with an IIoT deployment?
I would say all of them can already. Again, can you put a little bit of glue logic? I can't even keep up with, because I don't really care. I'm too busy doing my own thing. But there's lots of gateway. I just saw something from Dell, from IBM, from, oh my God, everybody. Everybody's providing that connectivity edge device that speaks Profinet or Ethernet IP on one side and Ethernet in the public domain on the other. So it's there. And absolutely, we and others are already designing products so that it's all intrinsically there. You just connect it and it's got a TLS encrypted authenticated tunnel to the internet, and you're done. And so that's there. It's here now. But I think the most important thing is for the user to say, well, where it makes sense, where's that place that's the farthest away? What's the place that I need most amount of access? Where would I like to historize and trend or do some big data analytics on the stuff coming from a heart transmitter because it's measuring a flow that's critical to a steam balance or something like that. Good operations, good engineering, they know where these tall poles are. So you can, for dollars, not millions of dollars, you can find these applications and start deploying a hybridized IIoT. In many cases, it's already happening. So just be smart about it. Get a few smart guys that understand the pieces of it. Go look on the internet and find out what's going on. And if you're using agents or unidirectional data collection devices or data diodes, you are almost immediately intrinsically secure if you're just pulling that data into some analytical environment. It's all here now. You don't have to rip and replace. You don't have to go crazy with this stuff. You just go crazy with the cost. You go crazy with the ideas. Go find these important applications and find the right way to get that data where you want it and where you need it, so you can reduce the cost of a truck roll. You can have a power or an oil and gas application where you got to get to it by a helicopter or an ATV or other things. You don't want to do that. You want to have as much diagnostics. So rather than costing $10,000 to get to a place, get the diagnostics and the technology there so you know exactly what's going on. So it's a case-by-case basis. It's an industry-by-industry basis. It depends on the vertical, depending on the user, depending on the site. It's infinitely variable, but everything you need to get started and really make a difference is here now.
Okay. Well, with that, we've reached our submitted questions and coming up on the hour. So time to thank our speaker, Albert Rooyakkers, our sponsor, Bedrock Automation, and all of you who joined us today. This webinar has been recorded and will be available shortly for on-demand viewing. The slides and assets from today's presentation will also remain available for on-demand viewers in the handouts area. And finally, did you like the presentation? Let us know your thoughts by answering our brief survey that will appear on your screen shortly. Your candid answers are not only appreciated, they help us craft future events. Again, thank you everyone for your attendance.
Thank you, Paul. And I'd like to say that anyone takes the effort to ask me a question or sends me an email, I will make the effort to respond. So, and everything that we've learned and everything we know, we write it up and we publish it. It's on our website. Go there and knock yourself out.
All right. Well, thanks again for your attendance, and everybody have a great rest of the day.
Thank you.